Thank you so much, and hope you all got my email that I already posted the finals.
Yeah.
Yes, thank you.
Oh, sure. So if you can do it, and again, this finals is comparatively, I should say, not too bad.
Mhm.
Yeah, that's what I think, but you can make to differ, of course. Uh, so let me open the PowerPoint so that you can see share application. Just oh man, it changed things completely. Okay. Can you see the PowerPoint, folks?
Yes.
Yeah.
Okay, that is great. Okay. Okay, so now we can start talking about. Tell me what questions you have. Let me check whether I'm recording or not. One more minute. I'm just stop sharing this for 1 second. I'll come back. Okay, I'm recording. Okay, I think you can see my PowerPoint right now.
Yes.
Yeah.
Okay, that's great. Now let us start.
Okay.
Anyone?
This is Nissa.
Yes, Nisa.
I was curious about, and maybe I just didn't, in the reading, I just missed it. But when in 6.2, when I look at number one, I mean, I'm having a great time solving for the constants. That's actually pretty fun. But in the first three problems, I guess I don't understand how I can just look at it and automatically know if it's linear or homogeneous or has constant coefficients. I feel like I'm missing whatever I'm supposed to do to distinguish that there.
Okay, so I'm going to talk about it. Okay.
Yes.
Okay, the windows, no. The definition of the homogeneous linear equation or not is this. If the equation looks like this, maybe if I want to use the same notations in the textbook, then you will not be confused, I guess. Okay, any equation which looks like this. Say this is called a linear equation. Any equation which looks like this is called a linear equation. And for example, in a sense, it almost looks like a sort of a straight line. That means the powers of this here, the CNs are constants, and these are some functions. And when you're talking about linear, all you really care about is you look the functions and they all should have power 1. Then you will call that as a linear. So linear simply means the power of all the functions is just 1. I don't care about the constants. What I mean to say is, for example, if you look at say 1a in 6.2, maybe let's do this. In 1a they mentioned is this: an is equals to 5 times an minus 1. I will look at the functions, that is an minus 1 and an minus 2. The power is just 1, so that is linear. And these constants can be numbers or not, I don't care about it. For example, if I look at say 1e in 6.2, this is 1a in 6.2, and I look at say 1e in 6.2, En is equals to 24 En minus 1 plus 22 E square n minus 2. Because of this square, this is not linear. And don't worry about homogeneous or anything. If you look into the same logic, if you look at one In is equals to 5 In minus 1 plus 3 power n In minus 2. I only look at these functions. I don't care about these numbers. These are coefficients, I'm sorry. This is also linear because this is power 1, this is power 1, this is power 1. So this is linear. So that is the definition of linear. Now, if I think about homogeneous, the definition of homogeneous is this. So the power of each and everything is 1. That is the linear. When it comes to homogeneous, the definition they have given there, let's insert a new slide. If you bring all the functions on one side, then the other side has to be 0. That means it should look like this. Then I don't care about these powers or anything at this point. If you bring everything on one side, the other side has to be 0. So if you look at, say, 1a, just this is what they had given to you. Now you bring all the functions on one side. So an minus 5an minus 1 minus 2an minus 2 equals to 3. This is not homogeneous because the other side is 3. So if you bring all the functions on one side of the equality, the other side has to be 0. Then that is going to be a homogeneous. For example,
in white.
I'm sorry, please, buddy. Just give me 1 minute. I'm sorry, guys. If you look at 1b,
Mm-hmm.
9b and I'm writing it back. So plus 9b n minus 2 plus 18b n minus 3 equals to 32b n minus 4. If you bring everything on one side, the other side is going to be 0 because this is a function, this is a function, this is a function. So this is a homogeneous, where the first one is not homogeneous because of this number 3. There is no constant like that, so this is homogeneous. For example, if you look at, say, 1g, now Nisa, tell me, is this homogeneous or not?
Yes, it should be.
It is a homogeneous, exactly.
Right, because I don't. Okay, good.
But if you observe 1b and 1g, this is a homogeneous equation with constant coefficients. The coefficients are all numbers, but 1g is a homogeneous equation with non-constant coefficients.
Right. I see that now. With the n squared, of course. So, all right, this makes sense.
So the procedures what you have learned is not going to work for 1g, but it works for 1b.
Mm-hmm.
So this is going to be a constant coefficients. So even if you see that, what do you think 1b is linear or not? Do you think this is a linear
1b?
equation?
Yeah. Yes.
What about 1g?
If I look at am I looking at just the functions? Or am
Yes.
I with the n squared with that variance, then it's not.
You don't look at the fun. You only look at the
If I look-
function. And you're talking about linears.
If I look at functions, then I would what? Say yes, right?
Yes, you're absolutely correct. This is yes.
Maybe I'm not seeing.
You're right. This is yes.
Okay, okay,
So both are linear.
okay, good.
But the first one is a linear
gotcha.
homogeneous equation with a constant coefficients. The second one is a linear homogeneous equation with non-constant coefficients. That is the difference between 1b and 1g.
Gotcha.
Okay. So, James, is that making sense, man?
Yes.
So, now if you look at 1i, I'm going to ask more. Let's insert one more slide. Now I want the answer from now I'm going to bother James. Now I want the answers for these things. Say yes or no. This is a constant coefficients. Do you think this is linear, man?
Yes.
Do you think this is homogeneous?
Yes.
Do you think it has constant coefficients?
No.
Awesome. So the procedure you have learned is not going to work for this in 6.2. For example, if you look at the first 1a, now James, do you think this is linear?
Yes.
Do you think this is homogeneous?
No.
No. And do you think it has constant coefficients?
Yeah.
Yes. Good job. If it is a non-linear equation or a non-homogeneous, the procedures involving generating functions and all to solve it due to time constraints. I thought I can go over that, but since it's an online class, I didn't have the freedom to finish all those things. To solve all these things, you need to do chapter 5 of generating functions and then go to 6.3. I know you don't mind, but yeah. Yes. So is there anything else which is going to be confusing in this? I want to confuse you guys, but you are not getting confused. Yeah, I think you're okay now.
I think so.
Yeah. Now, anymore?
We talk about question 18 and 6.1.
6.118. Let us look at that. Okay, in predicting future sales of a product, one assumption is to say that amount sold next year will be the average of the amount sold this year and last year. So I am calling like this, okay? There is certainly more than one reconciliation you can come up with. So the way I am doing it is, again, you can change all these things really. This year I am calling it as the AN, and the next year is AN plus 1. Again, you can change these symbols, and last year will be AN minus 2. Then the reconciliation simply tells you AN plus 1 is the average of AN and AN minus 1. And just let me make sure. This year and last year. So 2 times AN plus 1 is AN plus AN minus 1. That is the recurrence relation.
Okay. That's what I have.
Okay. Sometimes people take the nastir as an. Man, my battery is running low. It doesn't. Okay. Or some people will simply put 2an is equals to an minus 1 plus an minus 2. That is also gives the same thing. It depends
Okay.
on what is the symbolism. If you take nastir as an, then this year will be an minus 1. Last year will be an minus 2.
Okay.
Yeah.
What does it mean by solve the recurrence then if a sub 0 is equal to a sub 1 equals 1? What are they asking me to do there? Just find out what the plug those values in?
No. In a sense, yes. Solve the recurrence relation when a0 and a1 equals to 1. Let me clarify that for you. That means you are solving an equation for n. You are going to give a relation for n. Okay, let me see that. For example, in the textbook, I want to show you an example so you can easily follow.
Yeah.
Maybe I can solve this as well right away. That means they want to give you an equation for an. It shouldn't involve an minus 1 and an minus 2.
Okay.
So insert a new slide, and they have done lots of those things in the book. For example, this is what you got. Okay, let us use this relation 2an plus 1 is so, and they have given some things to you. In this case, they said, I'm sorry, I don't see those numbers right away. Yeah. If a0 is 1 and a1 is 1, what can you say about a2?
It'd be, so we're taking
Right?
those two together, it'd be 2. You know, we took an average in it. Okay.
That is
All
going to be 1, right?
1. Yes.
So if these two are 1, and what is a3 now?
Still gonna be 1, isn't it?
What is a4 now?
Be 1.
So I think the equation in this case is simply, that is just surprising. An equals to 1. That is the equation.
Okay.
That is solving. Normally, the typical way you should solve is this. Let me go to this is I got it, but the solving goes like this. Let's go to insert, and you should keep on going. Okay. Oh man, what is the plan? That is what you got, Nisa?
Yes.
So
Yes.
Okay, an is the average of the previous two. So that is what you need to write. So this is going to be a. You should get 1. Of course, that is the easiest way. I already solved it for you. But the typical way you should solve is you write an expression for an and you write an expression for an minus 2. An is nothing but the average of those previous things. So an minus 1 plus an minus 2 divided by 2. Am I correct?
Mm-hmm.
This is this year. Then this is the average of the previous twos. So now I will combine those two. So an minus 1 plus. Now I'm going to combine these two. This is what typically solving means. That means you are coming up with an expression for an or a plus 1 without involving all these things. So this is going to be 3 by 2 an minus 2. Now you will replace this with the previous 2. You will replace this with the previous 2. And you should keep on going until you are a0 and a1. But luckily for us, in this case, I think this is the easiest way. I am getting 1 each and every time.
Right.
Yeah,
Right.
so this is the way. Because going like this involves like, that is what I did. If you look into the videos, there are 1 or 2 problems which we worked out religiously.
Right.
Where you are not going to get 1. That is what solving a recurrence relation means. you need to give an expression for an like 2 power n times n plus 1 or something like that, which shouldn't involve the previous things.
Okay.
That is what solving means.
Okay.
That is what you did for in 6.2 couple of problems. You're solving for constants.
Okay.
Yeah.
Right.
Any more questions, guys? When I ask something is a solution or not, you have to just plug it and then check both sides are same or not. For example, in 6.2, 22 and all those things, you just replace an for 3 power n, and that should be 3 power n minus 1 and all, and that is solving. So right hand side equals to left hand side. If you show it, you're good.
Okay.
Yeah. If you have any more questions, I'm more than happy to solve it for you. I'm just asking.
On problem 16 and 6.1, I maybe this is asking too much, but I got 25 ways. Is that in the right ballpark with the postage stamps, the 10 cents, the 18 cents, and the 28? I mean, I don't know that I did it. I felt like I did the problem backwards. I felt like I was finally able to think about deriving the recurrence after I wrote down all the ways, and then I was able to go about it the other direction and go, yeah, this makes sense, because it kept breaking down.
I thought the answer for this at the back. Is there answer for this at the back? Yeah, it has
I don't
answer.
know what the back does on this. It might have.
Yeah, it has answer at the back. There are total 13 ways. Did you got it 13?
Boy, I had more than that. Maybe I misunderstood. I thought with the orders being that the order mattered, I had more than 13. Maybe I misunderstood.
Oh.
Ooh, they do have an answer. Yeah, I see that now. They have 13.
Yeah.
Oh gosh, they've got all of them right there. I didn't even see that. I have more than 13. I must not have understood this right.
Let me check. You have 10 cent stamps, 18 cents, and 28, each unlimited. Number of ways of obtaining n cents if the order in which they were clearly mentioned, order in which you put them counts. They clearly mentioned that.
Yeah. Boy, how did I? Maybe I overlapped and double counted some things because I wasn't. Maybe I've just missed that.
Yeah, that's what order really matters. Like 28, 28, and 10. If you take it, that is different from 28, 10, and 28, because both are giving you, yeah, really 58.
I see.
Yeah.
Boy, never mind. I didn't know this was all in here. I bet I double counted some, and I just didn't.
Yeah.
You know, then I just missed it when I did my, you know, when I was doing that, trying to go backward and then derive the recurrence, and I was trying to get closer to that. Okay.
Here, I don't think we can solve it, but that is a pain. Don't try to solve the recurrence relation. That is a pain. Because solving a recurrence relation is not an easy problem. Unless the recurrence relation looks a certain way, it is very difficult for us to solve. So unless they ask it, don't try to come up with the general answer, because if you can come up with a general answer, the advantage of recurrence relation is not in the first place. Because if you can come up with the formula, then what is the point of coming with the recurrence relation? Because normally these will be used when coming up with the general formula is very difficult. Yeah.
Okay.
Yeah. I want to make sure, do you guys know induction? I thought of putting some, but I don't know whether you did the mathematical induction or not. I didn't put it because it used a lot in solving a recurrence relation, but I haven't done that because I don't know whether you knew it or not.
Right.
Any more questions, guys?
I'm I'm still looking at my number 16, and I don't mean to be dumb here, but I don't understand why they don't have one that uses 118 and 128 and then 2 tens. Why isn't that a good way to make 66 cents?
Let me check.
That's why I have more than 13. I was looking at that trying to figure out why my answer was different. They use 2 18s and 2 28s, but since I have tens, I don't understand why I can't use 128 and 118 to make 46 cents and then use 2 tens.
Okay, FNB, and it's for 66. What did you say? Can you say it again? 128.
Yeah, they don't have listed 128 and 118 and then 2 tens. Because I would think shouldn't I be able to do that and then do all the different orderings of that, all the permutations of that?
They haven't given there.
They don't have that in their list. They have 2 28s and 1 10 written in all its different permutations. And then they have 3 10s and 2 18s and all the different permutations of that. If I'm looking in the back of the book there, I was trying to figure out why I have more than 13.
Okay.
I mean, I didn't mean to be stuck on that, but I just don't understand why they don't have that listed in there with answers. That's why I have more than 13 of them. That would be 46, right? And then I could just put 2 10s on there.
Yeah, let me check. But if you use the recurrence relation, use the recurrence to find the number of ways of obtaining a 66 cents of postage. Okay, so the recurrence relation says is this. Let me check. So if I want f of 66, if I can find the answer for 56, what is 66 minus 18? Okay, they are doing those 3 things. That is what your recurrence relation. So they did for this, this, and this.
Right.
Writing down ways. Okay, I think the reason is f of 10 is 1, f of 20 is, f of 10 is only 1. Okay, that is right. Oh, everything is unlimited supply too. Clearly mentioned. Okay. Huh. That is surprising for me. 28, 18. So this is going to give you another 4 factorial ways, which they haven't mentioned at all.
Yeah, they don't have that listed at all.
I was under the impression that
I mean,
they
it's
put it there.
not okay. I never feel like the back can be wrong. I feel like I'm messed up and I don't understand part of the problem.
No, we had a couple of places where at least I had seen back is not correct.
Yeah, like finding those constants in 6.2. I know those constants were wrong.
I don't think they were wrong. I think they factored out some things and canceled stuff. So
okay.
Yeah,
Gotcha.
so you will get it there. So, because constants can be simplified whatever the way you want. So that is the issue. But whatever we got is correct. Don't worry about that.
Okay.
28, 38, and 28. I want to make sure maybe I'm not adding things. That is 66. Huh. 28, 18, 10, 10. I thought somewhere I saw that. Yeah, they didn't put that. That is surprising for me. One 128, 118, and 210s. I don't know. I cannot give a valid answer here unless I'm missing something. Let me think about it. But I think you were correct there. I couldn't think of it suddenly. Why they can't do it? So if you arrange those things, that is going to give you another 4 factorial. So that should give you 13 plus 12, 25, isn't it?
Yep, that's what I have, 25. So, you know.
Yeah.
All right. Well, that's fine. I don't need a final answer. I just thought maybe you could point out something and say, oh, you're missing this, and.
I think they do miss it, but let me double check before I conclude, because sometimes I do believe the back of the book, couple of people will go through these things. But at least
yeah, right.
Unlimited supply, so that should work. They didn't put a restriction that there are only this many tens.
Right. I didn't see any restrictions at all. Just that the number of ways to obtain 66 cents of postage, and they said we had unlimited 28s, unlimited, yes, each and unlimited supply, limited on each. So I didn't see any restrictions. That's why I thought I could do that.
You should be able to.
Okay. Well, at least I know I'm thinking about it, in this way.
Yeah.
I agree. I'm right there with you.
I need to calculate all these 3 of them. Okay, maybe try 56 separately and 48 and 38 and see whether you're getting 25. I think you should get 25. Because this cannot be 13. 13 is really small. Yeah. I think I agree with you, Nisa. I think you are correct, but let me double check.
Sure. I can wait on that. That's no big deal.
Yeah, but I think you are correct.
Yeah.
It should be 25. I don't know, any more joined because I am on this PowerPoint. If anybody is there, any more questions, please.
I'm just joining late because I had no internet service until about 10 minutes ago. So I'm hoping to, yeah, Windows 10, I guess, did a lot of things to internet connections. And I just had to call my WCoil. I had to call my service and get reconnected. So I'm hoping, will you be posting this session very soon?
Yeah, I will be posting hopefully by tomorrow early morning, but there will be a long pauses. So I apologize for that.
Oh, that's okay. I'm fine with that. It's just I get so much from these sessions, and I tried to get on, and I finally had to call for assistance. They had to reconnect me, so.
Sure, I will be posting tomorrow morning. That's no big deal. But if you have any questions, please ask me now. I am there to help you out, so don't hesitate. I'm more than happy to revise if you have any questions.
Well, I had the same question as Nisa just did too, so that's why I was wondering. I just hoped I didn't miss too much else.
No, initially Nisa was asking, she was a little bit confused what is linear, what is not linear, and what is homogeneous. And that is what we talked first a few things. So do you have a question on this, or are you comfortable here?
Yeah, I just want to go back and listen to what you said, just so that's why I want to be able to listen to it tomorrow, so I can just go back and confirm and make sure I'm okay.
Oh, sure. Yeah, that is, I think that discussion you can easily get it just by listening to it. There were no pauses or anything. We just directly jumped in.
Okay.
And we solved a couple of problems as well. That you can get it right away. That's good. And any more questions? I know Nisa, you have any more, or James? Is it like Valerie I'm talking to? Because I couldn't see your name because I am on the PowerPoint. It occupied my entire screen.
I think it's just the three of us.
I think I'm good.
Tonight. Yeah.
Okay. Who is the third person who joined? Can you tell your name? I'm sorry, I can't see you here.
Okay, it's Pam Ripple.
Oh, hey, Pam. Yep, hi.
Hi.
And then we talked about the problem number 18 on 6.1. And
Okay.
this is the recurrence relation we got. You can see the PowerPoint, right?
Yes, I can now. Yes.
This is the recurrence relation we got. I've assumed AN is this year, AN plus 1 is next year, AN minus 1 is last year. If you take AN as this year, next year, then this would be the recurrence relation, depending on your symbols. If AN is this year, AN plus 1 is next, last year would be AN minus 2, then this should be the recurrence relation. If you take AN is the next year, then this year would be AN minus 1, then this should be the recurrence relation. Both are equally good.
Okay.
And we solved it and we got AN equals to 1 for all N. That is what we are getting constant.
Okay, good.
That is what we did.
I'm there with you. Good.
Yeah.
Okay.
Okay. And that is what we did. And then we talked a little bit about problem number 16. And you have any more questions, Pam?
No, that's where I came in, and I was questioning the same thing on 16 because I thought I'm coming up with something more, and they didn't have it listed, and I decided to go with my gut feeling instead of just listening to the book. But I'm curious to see if you're going to agree with that.
Yeah, it looks like we are getting 25.
Yeah.
Okay. Then we are all right. Any more questions, guys? And again, your constants can differ. Me and Nisa talked about for the last problem. I got different constants than whatever is in the book. That doesn't mean you're wrong. So I just want to put it up there. If you got the same constants as the textbook, good for you. But 26A and 6.2, I got a different constants.
Okay.
Yeah. So I got lambda 1 as 0 and lambda 2 as, maybe I'll write it down. I got lambda 1 as 0 and lambda
11.
2 11 over 18 and lambda 3 is negative 5 by 18.
Okay.
Yeah, negative 5/18.
Yes. Those are the things I got. Yeah.
Okay.
If you haven't tried that far, I'm saying. So the last problem, your answer might differ from the back of the book. Don't assume you are wrong.
Okay.
Yeah. And I don't see any discrepancies with the others other than the 16 thing.
Okay.
Yeah. I am pretty sure they missed it. So I am almost positive. I'm going to contact the author, but he might take a little bit of time to get back to me. Okay. James, you have any more questions, man?
I think I'm good. Thank you.
Okay. If you are good, you guys can leave and I'm going to post it. But Pam is the one who stopped late, so I'll just ask her, do you have any more, Pam?
No, I just, like I said, I just want to have a chance to go back and listen to the whole thing because there's so many times that just sitting and listening to this, I am, just watching it, I get so much out of it that things that I may have missed on my problems that I just want to clarify. So that's good. But yeah, I just didn't have internet for a while there, so sorry about that.
Oh, no big deal. And my request to all of you is please, I'm going to leave on like Saturday early morning for a vacation. So try to give the exams back by Thursday next week. That is the reason I posted finals already.
Okay.
Yeah.
Okay. Is it okay if it's late on Thursday night, the 15th?
Oh yeah, even I should say it, even if you give it to me like Friday morning, like 6 or 6:30, I'll try to grade it on that day. So even Friday late, Thursday late is absolutely fine. And if any of you want to talk a little bit about finals, we can do that Tuesday next week. But as I said, I'm not going to solve the problem for you. If you are stuck on something, I can give you hints. So let me know your
Okay.
thoughts. But that we have to do Tuesday next week.
Okay, if we let you know on Monday, is that good?
Oh, that is good. Even you can let me on Tuesday morning, also good.
Okay, that's good, because I
Even
just want to make
frankly,
sure I have a,
I can do Monday, Tuesday, Wednesday, any of those days. But as I
okay,
said,
great.
I'm not going to solve all them for you. That is sure. So you know that.
Oh, no, that's fine. It's just if there's something that I have a glitch on, I just want to be able to ask you, you know, a clarification or something. Yeah.
For sure. Please
Okay.
do that.
All right.
All right, that
Thank
sounds
you.
good. And
Oh,
and
anytime.
this
Take
assignment,
care, guys. Yes, ma'am.
and this assignment, we can turn this assignment in on Saturday evening, just so we have it in Saturday evening.
Yeah, I think the
Good.
due date is actually even Sunday is also good. That's fine.
Okay, good, because that's going to give me time. I just had to have grades in today, so yeah. So I'm still working on these, and all right, that's good.
Oh, thank you. Bye, guys. I'm going to stop share this.
All right.
All right. Bye-bye.
Bye.
Okay,
Bye.
thank you. Bye bye.
Thank you. Bye. I'm going to stop the record.